Hi everyone, it is nice to be here. As you already heard, my name is Marija. I am a senior ZK researcher in team 3227 in Ethic 42 company, but also I am assistant professor at Faculty of Mathematics in Belgrade, and I am also head of department for differential equations at the same faculty. But also, I'm co-founder of Mathematical Academy, and Mathematical Academy is some kind of private school where we are working with talented kids in the field of mathematics, physics, and cryptography. And for example, this year, our students, the best of them, obtained 41 medals on the state competition. So we are very proud of them. And also last year, with cooperation with Ethereum Foundation, we organized probably the first zero-knowledge proof course on Balkan. So today's topic is elliptic curve stealth address protocol. So let's start. We will talk today about private transactions. I think that everybody here knows that there are blockchains like Zcash and Monero that have some cryptographic methods at their core that enables privacy of transactions. But there is a great need to introduce private transactions on the public blockchains, such as Ethereum. So when we talk about private transaction, what we really want to hide? We want to hide the amount of transaction, recipient address, sender address, maybe all three stuff, but maybe one of them. And we can obtain this using different cryptographic methods. For example, we can use zero-knowledge proofs like Zcash, we can use stealth addresses, we can use ring signatures, or we can use fully homomorphic encryption. So today's topic is related to stealth addresses. And what are stealth addresses? We want to have the protocol like we have today, but we want to hide the recipient address. So, for example, we have two people, Alice and Bob. Bob will be a receiver, and Alice will be the sender. So, Bob first needs to generate some kind of stealth meta address, and he can send this stealth meta address directly to Alice, or he can add this stealth meta address in some registry. And after that, Alice can do some calculation and calculate Bob's new address, and she can send the money to this new address, and after that, Bob is able to control all the assets from this address. So every time when someone wants to send the money to Bob, he will use this stealth meta address, but Bob will obtain new address every time. Okay, so how we can achieve this? Well, we can use different cryptographic methods. One of them is Diffie-Hellman based. So first, Bob will generate his pair of keys, private and the public one. We know that we obtain the public key as a result of multiplication private key and the generator point from elliptic curve. Okay, so the public key will be the point on elliptic curve. And Bob will add this public key in the this registry. This will be stealth meta address of Bob. Okay, so in order to Alice to calculate Bob's new address, she will go to this registry and find this stealth meta address of Bob. She will generate her pair of keys, the private one and the public one, and after that, she will add her public key in this ephemeral public key registry and send the money to Bob. After that, Bob will calculate his address, and he can use this address and spend the money from this address. But we did not talk about how both of them can calculate this address, because both of them will calculate this address in different way. Okay? Both of them will calculate share key. What is the share key? The share key will be the result of multiplication. What is this? This is when Alice calculates share key. She will multiply her private key with the public key of Bob, okay? And Bob will calculate this shared key as a result of multiplication his private key with public key of Alice. But why this equality holds? Because here, firstly, we use that public key is a result of multiplication of private key and generator point from elliptic curve. And after that, we use just commutativity of multiplication of numbers. And after that, we then again used that result of multiplication private key and generator point on elliptic curve is a public key. So both of them can calculate this shared key, but in different ways. And for example, let's think about this, that shared key is, for example, the public key for this new address of Bob. There will be a problem because Alice and Bob both have different private keys, and both can spend the money from this address. And we want that only Bob can spend the money from this address. In order to obtain this, we need to include something in the private key of this new address that only Bob knows. So we need to include private key of Bob for his stealth meta address. So both of them, Alice and Bob, sender and the recipient, can calculate this shared secret and can hash the secret, but only Bob's know this little m, and this little m is private key for Bob's meta address. And we know that we obtain a public key as a result of multiplication of private key and generator point on elliptic curve. So when we multiply this with generator point, what we obtain public key of Bob, and this public key is in the registry, so both of them knows this public key, and of course both of them can calculate shared secret. In this way, we obtain that both of them can calculate the address, but only Bob can spend the money from this address. This is the basic concept. And we can add more things. We can add one more feature. For example, we can add the viewing key. So we can add little v and large v. What is the viewing key? For example, if you have a tax inspector and you want to prove that you paid all your fees for transactions, all your taxes for your transactions, well, you need to be able to prove this. And because of that, we include one more key. And this key we will give to tax inspector. And with this key, tax inspector can see all our stealth addresses, and he can calculate all the taxes that we paid for these transactions, for example. And because of that, this viewing key needs to be included here in the calculation of the shared secret. So this is just one feature in order to obtain that person who has the viewing key can calculate our address, but of course, no one except Bob can spend the money from this address. And we can add one more thing. What is it? We can add the view tag. We are adding the view tag in order to obtain that Bob can calculate his address in a faster way. So Alice, when sends her public key in the registry, she will add 1 byte of shared secret. So when Bob is finding his address, he will first matching his shared key with 1 byte. If there is a matching, he will calculate the address. And this is just for optimization. And as we already mentioned, there are different ways to achieve this and obtain stealth address protocol. This was the one way. This is Diffie-Hellman method that include multiplication on elliptic curve and hashing. But for example, here, my friend Mihailo and I created 2 new protocols that using elliptic curve pairing instead of calculation of share key as a result of multiplying scalar and point on elliptic curve. But we have two protocols. One of them is with double key, and the second one with single key. This one with single key includes only one number, and from this number you can obtain viewing key and spending key. So you have double keys, but just you have one number, and from this number you will obtain two keys. These protocols are really great protocols, but these protocols are not quantum resistant protocols. In order to obtain that we have quantum resistant protocols, we create, Mihailo and I, two new protocols. This ring learning with errors and model learning with errors, stealth address protocols. But of course, we can obtain post-quantum algorithm if we use fully homomorphic encryption, because the basic concept that we use in fully homomorphic encryption are learning with error technique. So we can do this in different way, of course. But today we will talk about elliptic curve pairing stealth address protocol. So let's explain what was our motivation. Our motivation was the paper-based stealth address protocol that was written by Vitalik and Tony and others. And they already implement these stuffs like this and this. They use dual key stealth address protocol. We talked about this protocol a moment ago. They use this elliptic curve and use view tags. But they also mentioned that they want to have on the top of this new protocols that using elliptic curve pairings or lattice-based schemes or to have post-quantum resistance. So this was our motivation. And because we are using pairings, we need to say a few words about pairings, and to fully understand how pairings work, we need to have deeply mathematical knowledge. So we will not go into details. We will just tell that we have one bilinear map, and the elements for this are subgroups of elliptic curve over finite field, and they have the same order. And G1 and G2 will be generators for these subgroups. And we will use here just property 2. What says this property 2? When we have S is the point on the first subgroup and T is the point on the second subgroup on the elliptic curve, A and B are scalars, so A and B can commute, okay, coordinately, and we obtain the same result as we pair these points S and T to the exponent of a result of multiplication A and B. So we will use this. So how our protocols work? We want to have the same structure as we had before, but here we can see, when this little key is private key for spending, and this little v is the viewing key. We will multiply a little key with generator point on the second subgroup on elliptic curve, but to get a large v, we will multiply a little v, the viewing key, with generator point from the first subgroup on elliptic curve. And we will add large v, a large k to this registry, and after that, sender will scan this registry, find the meta address, Alice will generate her pair of keys. The public key will be a result of multiplying this private key with generator point from the first subgroup on elliptic curve, and she will calculate the address as a result of pairing. So she will pair results of multiplying her private key with this public viewing key and public key of Bob that is in this registry. So she can calculate this public key in this way. After that, she will add her public key in this ephemeral public key registry, and of course the viewing tag like we had before. And Bob will calculate his address in a different way. He will prove that he has a spending key. The spending key will be a result of multiplication of a little key and a little v. So spending and viewing key, and only Bob's node spending key. And after that, he will calculate his address in this way. And both of them will obtain the same result because we use the property 2 that we mentioned a moment ago. So we had different technique, but we obtained the same result as we had it before. But now we can just say a few things about single key elliptic curve pairing protocol. So what we have here a little key. Little key is a spending key. Okay, this is a private key of Bob. But the viewing key will be obtained as a result of multiplication little key with generator point on the second subgroup. And the public key for this stealth meta address will be a result of multiplication little key with a generator point from the first subgroup. So we have viewing key and we have the public key, and this large V and large K will be in this registry. After that, we mix the technique that we had before in dual key stealth address protocol. And for example, we calculate S. S is not share key like we had in Diffie-Hellman approach. S will be a result of pairing. So we have that S is a result of pairing, but the public key of the address we can calculate like in Diffie-Hellman approach. And this is very similar that we already had. What is important here, that this will be the spending key for this new Bob address. And little key only knows Bob, so both of them can calculate this share key, but only Bob can spend the money from this address. And for the end, implementation results. We compare our results with results of dual key stealth address protocol without and with viewing tag. And the green is our implementation on elliptic curve pairing with double key stealth address protocol. And we can see here that we obtain the best results. This is time in milliseconds, and this is number of public key included in the ephemeral public key registry. So when sender wants to calculate his address in using elliptic curve pairing dual key stealth address protocol, he can do it in the fastest way. So this is very important. And this is a result for our single key protocol. We obtained the worst results, but I think that it is very interesting to have this as a concept, as theoretical result. So we can use single key in order to obtain everything we want, but we cannot do it efficiently. So this is everything from me for today. Thank you.
And you guys know what time it is. It's time for our Q&A. Do we have any questions for Marija? Perfect. In this front row.
Hi, thanks for the talk. What are the potential for this to be implemented, say, in Ethereum? Does Ethereum have all required cryptographic primitives? And if not, what is missing?
We are in negotiation with Ethereum Foundation to implement this. So everything is clear, and we're just waiting for them to implement this. Yeah.
Well, thank you so much.
Thank you.
And another round of applause.